Sign-in sheet back here. You want to either do it now one at a time or wait till you leave. Yeah, make sure you select the right date.
Do you want us to mark when you're online too?
No, just face to face. Yep. Yeah, just for the day.
Group A on Zoom today.
What's that?
Group A.
I'm not sure. Were you in class on Friday?
Mm-hmm.
Yeah, you'll be in Zoom. See a couple commercials. All right, a couple commercials before we start. Sent out a notification about the quiz. I don't know if anyone had any trouble in this class. I know the other section, there were some issues, and I was thinking it had to deal with them not knowing where it was, maybe just getting confused about the folders. But that wasn't the case. So I sent the email out, and I'm like, I'm gonna go back and look. Section 1 is where I created the quiz. And it was up later than what I wanted to on Friday because there was a technical difficulty with actually trying to upload questions because I have them all saved. And the new version is not allowing me to upload my original document, so I have to go through and type every question and every answer again. So I need to figure that out. So I created the quiz and then copied it over to this section. Somehow, some way, when it copied, it made it invisible for section 1, and all of the questions were gone. It didn't affect this section, and when I copied it back over from this section to the section 1, it was fine too. So one of the quirks of the new version of Blackboard. There's multiple of them. And the reason I talk about that is if you have any trouble with Blackboard or if you have any trouble with anything with the technology online, let me know. Try to let me know in detail if there's a picture you need to send me about an error that pops up. I've already made a list, a pretty extensive list of issues that I'm finding. They're fairly small issues, but those small issues start to add up with basically becoming annoyances. I know somebody was talking about having to refresh Blackboard for viewing something on Blackboard. I have it too. When I'm trying to upload something, it sometimes gets stuck in the upload. Sometimes if I do upload something and 100%, then I have to refresh the page to actually use the drop-down menus for the folder. So it's really finicky, I guess. Anyway. Also, I updated the roster in Blackboard, which was another thing that is strange. So I had to take out a bunch of people and then put a bunch of people in. So if I accidentally deleted you, let me know, and I will put you back in. I think if there's anything else. I'm also going to try to remember to record at least one of the sessions, either section 1 or section 2 of the lectures. The good thing about having this section is that if I forget to do it in the other one, I can do it in this one for what I'm doing now. And then I'm going to upload them to the YouTube page, just in case you don't happen to be here and still view the lecture. So, I think that's about it. Any questions? Anybody have? Sorry, anything from the virtual gallery? Okay. Share. Short review from Friday. So exercise science is an umbrella term, and going through the subfields and a little bit of specifics about what they entail, or at least general ideas. And then some of these fields are going to have even more fields underneath them and other specialties. Definitions, physical activity, exercise, and then sport and athletic competition, and looked at the activities of daily living, being an acronym ADLs, or ADL. So sometimes just daily living activities, but ADLs, you'll actually see it abbreviated that at times. A little bit of history, Greeks, Romans, we had a bunch of philosophers in there that loved looking at the human body, the human form. Different cultures love the human body. And we experimented sometimes, mostly dissection, about what was going on inside the body. Cutting it open, figuring out what are all these parts, what do they do. Eventually we found out, obviously, or I guess we might not have this class, but we found out what the parts did, how they interact with one another through basically a lot of experimentation and just studying what was going on actually inside of the body itself. The microscope being probably one of the best advancements in at least I guess modern human history. So being able to actually see tissues and see the cells, and then now we can see essentially the atoms. But seeing the tissues up close and the cells that actually make up the organs. And as we started to figure out what was going on with the cardiovascular system, the blood, the heart, we knew the heart beated. The heart beats multiple times per minute, as long as you're alive. So we have a heart rate, and then we have a stroke volume. And that stroke volume then is the amount of blood that's ejected for every heartbeat. So now we have a rate and we have a volume. And if we multiply those two things together, we can figure out how much blood is ejected from the heart per given time period, usually expressed in liters per minute. So an important component of trying to figure out, well, one is the heart functioning properly, and also how much oxygen we're using. There's another big component to this, figure out how much oxygen we're using, but that's a major component to it. Because the oxygen is floating around in the blood, and we need to know how much blood is there. So we started to figure out things like that. And recent influences then, physical education. In fact, physical education started in education, and then physical education come along. Then we started to develop exercise physiology labs, such as the Harvard Fatigue Laboratory. And we also started having standardized testing, physical testing for young children, maybe even high schoolers, push-ups, sit-ups, pull-ups. I think there's maybe even like standing long jump stuff, and I think there was maybe even get up and go tests and all kind of different tests that they would do, physical fitness testing, essentially. And then the professional organizations and associations were developed, one of the big ones being the American College of Sports Medicine. And reasons why it was there was so that it can give a good blend of physical education, medicine, as well as physiology, human physiology. And providing significant outreach, public outreach, and work to maybe push some public policies, create public health initiatives. But the big one of most organizations is disseminate scholarly research. So get out the new information that is being developed and studied within the field. And broad-based coursework, anatomy and physiology is the base. Understanding those two concepts, where the tissues are, where the organs are, what they're made out of, what the different parts are, and how they interact. And what is their purpose, what is the physiology with each of those organs and systems, and how those systems integrate into one another. Which we'll get into a little bit today and on Wednesday with chapter 3. Chemistry and biochemistry. Biochemistry being specific to living organisms, mostly relating to metabolism. And then human development and psychology, a little bit of math and statistics, and then physics. So you don't necessarily need to be a physics major or have a physics minor or math minor or major, but at least a little bit of background knowledge of those areas can certainly help. Sure. Then when it's the difference between graduate study, professional schools, won't go into too much detail on that now. Other careers, medical school, dental school, chiropractic medicine, physician assistant programs, and the two big ones, physical and occupational therapies. And you probably even add a third one there now because of athletic training moving to a master's degree, at least in the state of Ohio, pretty much all around the country. And what do healthcare professionals do? So you can pose for pictures in a clinical setting. So helping patients, and then any type of therapies that are there as well. So there we go. Chapter number 1. Over and done. So just a short review in case you forgot. And let's start chapter number 3. A systems approach. So we're going to look at most of the major systems of the body. Well, what they are, what's kind of the main function, maybe some certain parts, and then maybe a couple fun facts about them. Fun facts being maybe an adaptation or a response, maybe something about diseases that could develop, and potentially show a picture of an Austrian bodybuilder at some point. Okay. Systems of the body work to respond to, you can sum most of these up. In fact, one of them is actually named this, stress. Either physical or psychological stress on the body. Physical activity isn't always thought of as a stress, but that's what it is. You're putting stress and strain on the body, different body parts. Now, it's usually seen as good stress because the body can respond to that and become healthier. Different parts can become healthier. It can help reduce the risk for certain diseases, become more physically fit. Same thing with regular exercise. So it works to respond to these two, I guess, good stresses, if you will. Now, there could be additional stress you're placing on the body if there's some type of over-exercise. That's somewhat rare, somewhat. And if you're doing exercises incorrectly and putting undue stress on certain joints of the body, then there could be issues. But we're talking about just normal conditions, nothing out of the ordinary. Also, just general stress, and this is related to the psychological stress that we can have in our lives. The stress of exams, going to class, a pandemic, whatever it may be. Any changes in nutritional intake. This can be a big one that we sometimes might not think about. If you're normally eating, I guess, fairly healthy foods throughout most of the days of the week, and then all of a sudden you pig out on some McDonald's or whatever it might be, the body's going to be shocked a little bit. Digestive system may be a little bit perturbed. Yeah. Because of some of the nutrients within some of that food, fast food mostly, highly processed food, it can cause some issues, especially if it's eaten often. Not just often throughout the day, but often throughout the month and the year. So intaking a lot of salt can increase blood pressure, a lot of fat over time then can cause heart disease, sugar can cause problems with the cardiovascular system, potentially leading to maybe weight gain from that as well, and then leading to other issues. And then environmental conditions. And these extreme environmental conditions can be heat, can be cold, can be low oxygen. Where do we see low oxygen at? Or get low oxygen?
The higher you go up.
Yep, the higher you go up. So going up in altitude. So the air is quote unquote thinner. It's just spread out. All the air molecules are spread out. So for each breath you breathe, there's less oxygen molecules. So the body's going to respond to that. Hopefully there's an adaptation that occurs if you're there long enough. But that adaptation takes a while. It takes 3 weeks or so. But the heat you can adapt to. The cold, not so much. Our bodies don't like adapting to the cold. We will get used to, it's basically a habitual adaptation, meaning that we do things to keep ourselves warm. We'll put on more clothes, we'll build a fire, we'll go inside somewhere, we'll drink hot cocoa, whatever works. Could also be humidity. And then if you add in heat and humidity, now you have essentially two different stressors. Because with the humidity, the problem is we need to be able to dissipate the heat from our bodies through evaporation. But if the air is already saturated with water at a high amount, the water that's on our skin cannot evaporate. So then we have a problem. We continuously sweat, but we can't evaporate the sweat. So it causes some issues with regulation of our body temperatures. But anyway, all of this is basically responding to a, hold on a minute. I wish we had the smart board here where I could just go up here and write in my finger like in the other classes. That would be kind of nice. All of this is responding to a change in what is known as homeostasis of the body. Here's the .di. Homeostasis of the body. Oh, there should be an O right there. Sorry. Look, Bob, look what I drew. Oh my goodness. Homeostasis. Essentially an even keel of the body and the physiological parameters. Heart rate, blood pressure, hormonal levels, breathing rate. All of these stresses will change the homeostasis of the body. In terms of physical activity and exercise, say you start exercising and you're at a certain intensity and you stay there for 2 or 3 minutes. You will now have a new homeostasis, usually, at least with a couple different data points. Heart rate and blood pressure being the big ones. Even breathing rate is going to be about the same. So it's going to increase over a few minutes time, heart rate, blood pressure, and then it's going to level off. And as long as you don't increase or decrease the intensity and maintain the intensity all throughout, it's going to maintain that level. So it's essentially a new homeostasis until you stop exercising, and then it's going to gradually go down to what we refer to as resting levels. Hopefully it goes down to resting levels. If it doesn't, then we got some problems. Questions so far? Nothing online? Then any disease conditions that we may have are going to cause stress. Stress on the body as a whole can cause psychological stress as well, but also the specific parts that those diseases will be affecting. And usually it's not concentrated on just that area that's going to be affected. If one system is stressed, it's going to affect all the other systems that are integrated with it. Alrighty. So important for exercise science professionals to know the knowledge of how all of the systems function. All the different parts, all the pieces, how they function, but also how they're integrated, how they relate to one another, how they work in conjunction to make sure that we are staying alive and get to as close to that homeostasis as we can get. So there's a figure in your book, figure 3.1, if you have the book that I will show right now. Going through pretty much all the systems. We're not going to go through every single one of these, but we'll go through some of the major ones here today and on Wednesday. So you can look at a little more detail on the descriptions of them, but we'll talk about them. We'll go over them. Start off with the nervous system. Good one to start off with because it controls everything that we do. It even controls itself. So there you go. So the primary component is the nerve cell, or otherwise known as the neuron. And it responds to acute changes in the body. So acute changes being there is some signal coming from somewhere. It could be outside of the body or it could be inside of the body. And those signals are going to be going back to the brain via the nerves and the spinal cord. And the brain's going to figure out what needs to happen. So for instance, if you step on a nail, that signal is going to travel from your foot all the way up through the spinal cord to the brain. The brain's going to say, okay, this isn't good. Something's a little wrong here. It's going to figure out what to do, and it's going to say, I think we need to take our foot off of that piece of wood or wherever the nail is and get away from it. So it's going to send the signal back down to the muscles of the legs and of the foot to contract, to move the leg out of the way. Hopefully it doesn't take that long. Hopefully it's much, much quicker. Some facts or some key considerations. There are disease conditions that are going to affect the control of the nervous system. Parkinson's disease being one of the big ones and one of the more debilitating ones. There are many others, but Parkinson's disease is a good example. So the nervous system basically helps us function throughout all movement. So in sports performance, it's helping us to control our movement. This is where some adaptation can occur, some long-term adaptation, just not acute changes, but actual long-term adaptations can occur. We can learn new behaviors, learn new actions. That's how we learn how to throw, and maybe throw accurately, throw baseball, softball, football, whatever it might be. Or actually learn how to do a somersault or a twirl or do something maybe related to gymnastics, which is an amazing thing to see in person. Little side thought of the day. Go to YouTube and look up like the old time gymnastics, specifically I think the floor exercises. I think I could have done some of that stuff, but at least maybe a little bit of practice. I mean, it was slow. It was like just somersaults and just looked like kind of slow, like interpretive dance. Now it's like fast paced and you got multiple flips at a time, and it's kind of amazing to watch. Anyway, it's just something. A little bit of nostalgia. But those movements can be learned over time. That's the motor behavior, motor learning aspect to it. The other thing too, yay, we got the mower. Yay. Yeah, I think it's mower. The other thing too is that there can be a learned response when we start to maybe weight train. There's one specific adaptation that is, actually I'm going to keep this in here. I'm not going to try to type all that out. Oops. Okay. Neuromuscular adaptation. Anyone ever heard of this term, phrase? Yeah. Neuromuscular adaptation is kind of what it sounds like. There's an adaptation of the nervous system in conjunction with the muscle system. During the first, anywhere from 6 to 12 weeks of initial weight training exercises, this is actually seen quite often. During those first couple months of weight training, consistent weight training, at least a couple of days per week. You can't just be, you know, you're gonna start today and then a couple of weeks from now you do another routine and then a few weeks from then you do another routine. It's a consistent routine. There is an increase in the strength that is gained throughout those 2 months, but there is very little muscle mass that is gained. So you start to think, well, if there's hardly any muscle mass, then what's the strength gain? It's actually coming from this. The signal at the beginning from the brain to the muscles that are being used is somewhat disorganized. It's not coordinated. The brain doesn't necessarily know which muscles to fire at exactly the right moment, and it can be a little off, and it can start firing the wrong fibers. During this period of time, there's an integration of the signal from the brain to the muscles that are being used, to where the brain starts to send signals to the correct muscle fibers in the correct order. So it becomes more synchronized, it becomes better adept to telling those muscles to fire at a certain point in time, and all of that together creates just a more efficient movement, a more efficient muscle contraction, thus increasing the amount of weight that can be moved, so strength. Even though there's very little muscle mass actually being gained during this time period. Now, after this occurs, then it's pretty much all muscle mass that's causing the increase in strength then, after that. So that is one adaptation. So we can already see an integration of two systems. We get the nervous system and the muscular system. Yep. So the nervous system separated into a lot of different divisions. The two big ones, the central and the peripheral. Sometimes abbreviated the CNS and the PNS. Okay, usually I get a couple giggles from that one, but it's, never mind. Maybe not a good joke for a Monday. Central nervous system is the brain and the spinal cord. The periphery is everything else, branching off from that. Speaking of the periphery, we got two different nerves. One's coming in, the other one's going out. The stuff coming in is the sensory, so the stuff that we sense. It can be within our bodies, or it can be outside of our bodies. So touch is one of those sensory nerves. Then the motor is the stuff that is going out. The information going out to the muscles, going out to the organs, to do what they need to do. And the motor is separated into two. Again, we got the autonomic and the somatic. The autonomic is what it sounds like. It's automatic. We don't have to think about it. Heart rate, digestion, hormone releases. We don't have to think about this stuff. It just happens. Now we can think about something that increases our heart rate or our blood pressure, but we don't have to actually contract the heart. We don't have to try to squeeze the chest to contract the heart. Now, if somebody is passed out and going into cardiac arrest, then maybe we can jump it somehow by pressing on the chest, but that's something somewhat different. We don't have to think about our heart beating throughout the day. We don't have to think about blood pressure changes throughout the day. They just happen. We don't have to think about digestion. Thank goodness. We don't have to think about, okay, Food's now in the duodenum, we need to get it down and squeeze it just a little bit more. Okay, don't have to think about it. Separating, or the divisions here that are separated are the parasympathetic and sympathetic. Anyone know what phrases are used to describe these two? In which ones? Anyone ever heard of them? Sympathetic is the fight or flight response. So this is where you'll have an increase in heart rate, blood pressure, breathing rate. It is what it sounds like. If you are being attacked by a grizzly bear, your body's going to react with this system, the sympathetic nervous system. Same thing also happens during exercise. Now, the parasympathetic is completely the opposite. This is known as the rest and digest phase. Meaning that we're rested, our heart rate is low, blood pressure is low, breathing rate is normal. We can digest food more efficiently. We're calm, nice and calm. On the somatic side, this is the stuff that we can control, mostly the skeletal muscles. We can control which ones we contract, we can control how fast they contract, and how much strength and force we can apply. So these are the ones that we normally think about. Now we might, if an action becomes just natural to us, we don't necessarily consciously think about it in the way we normally think about consciousness. Okay, I want to contract my bicep, and then we do it. It's just kind of a natural thing, but we can control it is the major point there. As long as there's no disease conditions that are causing a disconnect there. Or injuries. Injuries can cause them to not function also. Any questions? Nervous system. All right, moving on to the muscular system. Primary function here is movement, such as in a barbell curl. Here we go. There's the Austrian bodybuilder. There are videos online of Arnold Schwarzenegger in Austria giving interviews in his native language. I think you can understand him better when he's speaking a foreign language than you can when speaking English. Like he has his own accent. Like it's weird. Anyway, strange things. So primary function is the movement. The component, the big component here is the muscle fiber, or the muscle cell. Protein, basically. 3 types of muscles. You've got skeletal, which is the stuff that you'll see here in the picture, or at least what's underneath the skin. And the cardiac, which is only found in the heart. And then we got the smooth muscle. Where is the smooth muscle located? Anyone know? Smooth. Mostly found in blood vessels, in the walls of the blood vessels, as well as the walls of the digestive system, of the tube, essentially, of the digestive system. And here's a drawing that you will see in pretty much any exercise science, exercise physiology book, anatomy and physiology book. Something similar to this, showing a muscle cell and some of the basic parts of it. The big parts, the real important stuff, is when you get down into, you see these little jagged lines? You got them right there. And you got another one over here. Whoops. So from here to here, when we contract our muscles, this is what's contracting. This little guy right here. The thing is, there's just not one of them. There are hundreds of them, thousands of them, tens of thousands, possibly hundreds of thousands, depending on how long the muscle fiber is, that are all contracting at once. And all of those contracting at once causes the entire muscle to shorten or contract. And it's a pretty simple process when you look at it. I mean, when you get into the finer details of it, it can be somewhat mind-boggling, and I tend to geek out on it. But this is essentially muscle contraction in a nutshell, at least the components of it. You got one protein right here, and you got another protein located here. Whoop, I'm getting a little offline. So you got the one, it almost looks like a little double helix, and then the other one looks like a centipede. Those two proteins just slide across one another. That's basically all that's happening. Simple. Now there's other parts to it. If you want to look at it a little bit more, if you, well, you can go online and look at animations of it and look at some of the details. There's two other proteins that are actually kind of important to this. These two guys up here. And there's one mineral that is actually very important in all of this, and that's calcium. If we didn't have calcium, we wouldn't be able to contract the muscles. We normally think of calcium being the major portion of the bones, which it is. But calcium is so important to muscle contraction that if we don't get enough calcium in our diet, the muscles will actually steal it from the bones. Then we can maybe develop a certain disease if we steal too much of it. That's about as detailed as I want to get for muscle contraction. Looking at muscles specifically, some divisions here with the muscles. There's two basic types, type 1 and type 2. Type 2 has kind of two subdivisions of them. Type 1 is mostly used for long distance. It's comparatively weaker to type 2 in that it doesn't produce as much force. It's a little bit slower to contract. It's a little bit slower to develop muscular force. But it does not fatigue nearly as quickly. It takes a long time to fatigue type 1 muscle fibers. And depending upon how trained somebody is, they can, I mean, theoretically go on for almost forever. These are the muscle fibers we use most of the day. Type 2 muscle fibers, we'll use some of them throughout the day, depending upon what we're doing, too. If we're just laying around in bed or on the couch all day, it's mostly just type 1 muscle fibers. If we're weight training, or maybe we're out doing lumberjack stuff, then maybe we're using some type 2 muscle fibers. A lot more. Sometimes you'll see color differences in them, especially if you do chemical assays on them. But the type 1, sometimes referred to as red muscle fibers, the red type. That redness actually comes from hemoglobin, or myoglobin, excuse me, which is the blood cells, the oxygen-carrying blood cells of muscle fibers. The type 2B, those muscle fibers are used for very high-intense activity. I mean, very short, highly explosive movements. They tend to be white in color when you're doing some type of analysis of them. And that's because they lack oxygen and lack the oxygen carrying capacity. You actually see this often in the differences between a wild turkey. So we've all probably seen at Thanksgiving, and I have this nice white, bright white, butterball turkey. If you've ever eaten a wild turkey, not drank wild turkey, it's something completely different. Ate wild turkey. The meat is darker. It's usually because it has a little bit more red or type 1 fibers. The reason is because turkeys that you buy at a store, they're pretty much at farms, and they don't need to fly, all that, at least hardly any. They're usually in kind of big groups and just stand there basically and eat all their lives. Wild turkeys actually have to get away from predators sometimes. So they actually do have to fly. They got to use the breast meat. They got to use their wings. So they got to use some oxygen to get away. So their meat is darker. To me, it tastes a little bit better. It's got a little more flavor to it. Anyway, if there's anything else here. Oh, I hate confusion, but type 2B is also known as type 2X. What's the publication date on this book? 2017, 2018? No, the PowerPoint was 2018, but it's actually rare to see type 2B nomenclature. Most textbooks now are referring type 2B as type 2X muscle fibers. They're the same thing. Why the change? I don't know. It happened about 15 or so years ago. There became a transition from calling it type 2B to type 2X. Again, I'm not sure why. Maybe there is some other delineation. A and B sounds pretty simple to me, but sometimes I think scientists get together and they're like, hey, you know what would be really fun? This is already confusing enough for some people. Let's take it a step further. Let's start changing names and stuff. When you get into metabolism, it gets even worse, especially because there's a cycle in metabolism to help use glucose for fuel, or sugar for fuel. That cycle is known as the TCA, or tricarboxylic acid cycle. It's also known as the citric acid cycle. It's also known as the Krebs cycle. All three names describe exactly the same thing. So instead of having one name for it to make it nice and simple, we got to have multiple names for it. Anyway. We'll move on. Any questions on the muscular system? Okay. Skeletal system. So providing a framework, structural framework. It's our scaffolding. There are parts of the skeleton that help protect organs and other tissues. The skull helping to protect the brain. The vertebrae helping to protect the spinal cord itself. The rib cage, helping to protect the lungs and the heart. Also provides a nice lever system for movement, so the muscles attaching to the bones at certain points, allowing for a lever to be created so that we can move the bones, thus moving our bodies. Also helps for a little bit of a storage area for certain minerals. What minerals would be stored and used in the bones? Want to name any? Anyone online? Yeah.
Calcium.
Yeah, calcium. Calcium's the big one. Calcium's the big one. That's going to be the big component of the muscle, or the muscle, of the skeletal structure. Anyone know of any more? Here's a couple other ones. Phosphorus, magnesium. Those are the big ones. Also in the middle, going down to the primary components, but the minerals, the cells, the actual, what's known as the osteocytes or the bone cells, and also bone marrow, which is where blood cells are created. So now we have an integration of the bones to the cardiovascular system. And really all the tissues. If we didn't have hemoglobin or red blood cells, we wouldn't be able to use any tissue. It would die. Tissues need oxygen. And we're constantly getting rid of red blood cells. They're destroyed and then created. Destroyed and then created. And referring back to the muscular system, with the calcium being needed, it's going to be taken away from the bones if we're not getting enough in the diet. The problem is what can happen is we develop osteoporosis, which is essentially a weakening and deterioration of the bones, causing an increased risk for fracture, even just fractures under little amounts of stress. And even stress fractures in multiple places. The good thing is, as long as there's not some other serious condition that's causing the osteoporosis and it's more nutritionally related or physical activity related, it can come back. And I mentioned physical activity because the bones act just like muscles do. You put stress on them, there's going to be a response to build the bones up stronger than what they are, or at least keep them strong. That's why astronauts, when they go into space, they got to do some type of weight-bearing exercise. They have different devices on the International Space Station where they can do some weight training exercises to have some stress on the bones. Because if you don't have any stress on the bones, and if they're just floating in space for a year, their bones are going to be osteoporotic afterward. Even though they might get enough of calcium in the diet, the bones are still going to be weaker because they haven't been stressed. So very important for astronauts to do some type of weight training, which is essentially somewhat simulating gravity. I mean, as long as we're walking around, we'll be okay. It's not like you have to do weight training to have strong bones, or to at least have strong enough bones where they're not going to break and be osteoporotic. But weight training would definitely help. Any questions on the skeletal system? Okay, that'll be it for today. We'll end there. It's where I stopped in the last section. Anyone online have any questions, anything? I'll see you guys on Wednesday. Don't forget to sign the sign-in sheet in the back. And if you have any questions, yeah, so if you have any problems with Blackboard or anything like that, please let me know in detail what's going on at any point in time. That way we can get it fixed, remedied as soon as possible. If not, I'll see you guys later. Bye.